In this video, I'm going to show you how to run a basic regression in R. And we're going to have two predictors in this particular regression, and we're going to have to do a little bit of recoding in order to make one of the variables appropriate for regression. We're going to be using some data that I pulled from the PISA 2012 dataset around students' math achievement and some of the contextual variables that they collected via survey. So I'm going to give you a few seconds to get our studio pulled up and ready to go, and then we'll get started. All right, so in R, if we're, first of all, we're going to be using these packages, at least these are the ones I suggest. We're not going to use all of them in this video, but these will be important for checking assumptions later. The Rio package for importing, tidyverse for plotting and doing some data manipulation, the car and psych packages to help with descriptives and some other assumption checking. So make sure to initialize these and then import your data set. I've just called my data set PISA. And the names of these variables, so we have C and T as country. We'll be using PV1 math because the question that we're going to investigate for this video is what influence does SES and students' home language have on their math achievement on PISA 2012? So plausible value 1 math scores. ESCS is SES, PISA's measure of SES. And then the other variable that we're going to use in this video is ST25Q01, which asked students if their home language was the same or different than that of the test that they took. So those are the ones we're going to use. If we look at the structure of these variables, we'll see that PV1 math is numeric. That's what we want. ESCS was imported as numeric, and ST25Q01 was imported as numeric. So these are important things to note. However, if we look at a table, and so I always start by doing this because I know ST25Q01 was just 1s and 2s and NAs. Not applicable or missing data, meaning that the student didn't respond essentially to the item about language. So PISA $ST25Q01, and then I put this here so that I can also get a look at how many were NA. So basically this is just going to give us a quick look at the data. So we have 57,362 students who said the language was the same, their home language was the same as that of the test. And 6,100 students said it was different. So definitely there could be some problematic things here to look at in terms of assumptions with this highly imbalanced subsets. And 2,073 were missing for some reason, and there's multiple reasons that it could be missing, but the biggest one is just that it was left blank. Okay, so what we need to do though is change this to be 0s and 1s in order to use it in regression. Because regression requires continuous data, and so we have to sort of trick the regression in order to help it assume that it can make this assumption. So the easiest thing to do would just be to make the 1s 0s and the 2s 1s, because if we want to do that, we can just subtract 1 from every value. So 1s become 0s and 2s become 1s. You could also do this with an if-else statement. This case, I find it a little more straightforward just to change it, and I'm actually going to give it a new variable name called lang. And the reason for this is then I can check to make sure that everything translated correctly and I didn't miss something. So I'm going to create a new variable. So PISA $lang left arrow. And then I'm just going to put here, and I put this in parentheses just so you could see it a little easier. I'm going to take the st25q01 language variable and simply subtract 1. So if we run that and then create a table with the new variable lang, comma, the original variable, we will see that the original variable is the columns. That's the second thing that we put here in the table. So what originally was a 1, all of those became zeros. None of them became ones, and if they would have become something else, it would have showed that here too. And then the 2s, which were different, all of them became 1s. There was none of them that became 0. So it looks like everything translated correctly, and it matches up with these values that we had at the beginning. So it worked. Okay, to run a linear regression in R is very straightforward. We simply, I just am storing the regression in the word model, just so that we can extract things from it. And then the function that we use is LM. It just stands for linear model. So first we're going to put PV1 math, PISA PV1 math, that's the outcome measure, and then tilde. Tilde in R means by, and in R, the equal symbol can't be used like it would be in a regression model. So and it means to define something, and a double equal sign doesn't exactly make sense either, because that's used as more of an operator to tell if two things are equal to each other or not. So we're going to use this tilde, and then put in, and you can just hit the return key or enter. And I do this so that I can put comments here to remind myself what these variables mean. So this is students' math scores. And then PISA ESCS, that's their SES measure. If you wanted to look at gender, you would need to make this be 0s and 1s. But I just want to put that out there, that that's the other variable that I pulled out that could be used here as a dichotomous variable. And then, so you can skip that line. And then PISA LANG, that's the new language variable. And remember, 0 means same, 1 means different. So if we run this, it stores it in the word model. And then we want to get a summary of that model. So just put summary, and in parentheses the word model that we stored the linear model into. And it will show us the outcome measure, or the output here. You can see a quick look at the residuals, although those are also stored into that word model. I can show you that in a moment. So if you wanted to just pull the residuals out and look at a histogram of them, we can do that. The coefficients here, so we see PISA ESCS has a coefficient of 35.77. And so remember that ESCS, first of all, is a standardized variable at the global level, not necessarily for this group. So a 0 means the average SES across all the countries that participated, and a 1 is the standard deviation for all of those sets of countries. So when we're interpreting this, an increase of 1, which is an increase in the standard deviation for the world, is associated with an increase of about 36 points in students' math scores on the assessment. And that seems like quite a lot. Actually, if we run a summary here in a moment of the actual, to look at the descriptives of PV1 math, you'll see that the standard deviation is about 95 points. So this is about a third of a standard deviation increase. It's pretty significant. And we can see, of course, it is statistically significant. However, we have a very high sample size. I don't think it's showing it in here. But if you look down here at PISA, we have over 65,000 rows. So over 65,000 students are in this data set. So that does increase the chance of a statistically significant result. So we're going to learn about in other videos how to temper that and make sure that that isn't happening just because the sample size is so large. And then here's our language variable. We see a coefficient of about 9. And remember, these are zeros and ones. So students whose language is different, who have a 1, right? Whose language is different than the test, score about 9 points higher on the test than students who don't. And you can still see it is still statistically significant. And for those of you wondering, this E minus 15, E minus 16, that is the scientific notation. Basically, it means 2 times 10 to the negative 16. In other words, imagine decimal point, 15 zeros, and then a 2. Or in this one, decimal point, 14 zeros before you get to that 1. So very small p-value. Okay. And then at the bottom is where we can get the multiple r squared value, 0.228. If you want the actual r multiple correlation, just take the square root of that. So about 22.8% of the differences that we see in the students' math scores can be explained by the combination of SES and students' language being different or the same as the test. And then we get some information from the ANOVA test here, an F score of 9,334. Here's the 2 sets of degrees of freedom, and a very small p-value indicating that the model is statistically significant. So there you have the regression. And we have a few things that we can look at now that we've created this this model. So one of the things that we can do is simply look at some plots of the model to help us interpret whether or not it was appropriate. So was a linear model appropriate? So if we just type plot and model, it's going to ask you, so you have to come over here and click and hit enter. It's going to plot these one at a time. And it's being a little bit slow here. They'll eventually pop up as we go. And these plots are helpful, and I'm going to show you how to get them all in one screen. It's kind of annoying to see them all separately like this when they're all telling you similar types of information. So you can click this little arrow and go back and look at these other plots. But something that's more helpful is a function called par. And what this does is it tells you that you're telling it to put it in a 2x2 matrix. So 2 rows and 2 columns. That's what MF row equals C 2 comma 2 means. 2 rows, 2 columns. So if we run this, and it gave me a plot rendering error. I'm going to make this a little bit bigger here just so that it has some space. Once you run that, then it's ready to put this in a matrix form so we can run plot of model again. And it will put them on a 2x2 grid on the screen. Okay, while we're waiting for that to pop up, I mentioned being able to just look at a histogram of the actual residuals. So one thing you can do, if you type str and look at model, and this is going to take a minute to pop up while we wait here. All right, I'm going to stop this from running. Okay. Just because it's taking a little too long for my processor to do that at the moment. Okay, so if I type structure of the model, you're going to see all the different objects that are in here that we can extract. So scroll up to the top. There's a lot of things in here. But you'll notice, so we have the coefficients. We could just type in model dollar coefficients, and it would just spit out the coefficients for each of the variables we have. But the other thing we can do is just pull out the residuals. So if we just want to look at a histogram of the residuals, something really simple we could do is just type in model dollar residuals. And it doesn't like how small this was. Hold on. All right. Give it a second. Remember, it's trying to render this plot that has almost 65,000 data points in it. So it's taking some time. Okay, so I had to take a little break there because my processor was getting really bogged down. But while I took a break, I got this pulled up here. These are the 4 plots that would have pulled up from running these 2 lines. And you'll see in these plots here, the normal QQ plot, you should see this to be essentially a straight line, and there is a dotted line there through the middle, and it does look like things are the way they should be. The residuals versus fitted, basically you should see a flat line. It's got a very slight curve to it, but it doesn't look like there's anything there that is problematic. And so those 2 plots are really the ones that I want to focus on right now without digging too far into depth. Things look like they should be linear. However, the other thing, like we talked about before, I had some processing issues, was looking at this histogram of the residuals. So in order to do this, we want to reset this to not be a 4x4 grid, but to just allow 1 plot per screen here. So if we put this in and tell it to do one row and 1 column, and then we run the plot again, you'll see the histogram of the residuals, and we should see this normally distributed in order to tell us that a normal model was appropriate. So this is just another way that we can examine that. And of course, we can use things like ggplot2 in order to make this look more professional and add some other elements to it, like the normal distribution line through it, so we can make some better judgments. However, looks pretty good, so no problems there. And of course, we could also run some descriptives. So we could use the describe function from the psych package to look at the descriptives for PV1 math. We could also run this to look at the descriptives for ESCS. And we could run some normal distribution tests like the Shapiro-Wilks test and things like that, and look at some histograms of these things in order to examine that. And remember, the language one is dichotomous, so looking at that and trying to understand normality is not part of the assumption checking. However, it is nice to be able to see that as fairly well balanced. And in this case, we do have some imbalance issues that could cause some problems. However, regression is fairly robust against that. So hopefully this helps you get an understanding of how to start thinking about multiple regression in R. And let me know what questions you have.